So today we're going to continue our discussion of conformers. Remember, conformers are our way of looking at the same molecule presented in different geometries or different orientations. What we're talking about, like remember, this is in the class of things when we start talking about how a molecule looks. What we have to do now is we've talked about, how to name things. You've got your IUPAC naming part. We know about bonding. Next part we're going to talk about is the same molecule but presented in different orientations. What's happening there is rotation about a single bond. There are ways of showing that a molecule looks different because rotation about a single bond allows it to have a different presentation. These have different energetic consequences. Having a different rotation or a different alignment of certain bonds in a molecule has different energies. So we defined this last time looking at simply ethane, 2 carbons. We have a Newman projection, that's what we're showing up here. This is how we look down the axis of a bond and actually record easily in 2 dimensions what this rotational angle is. We define a dihedral as basically taking 2 planes, carbon, hydrogen on the front, carbon, hydrogen on the back, and the angle that those 2 make with each other. Remember, we called staggered structures. Staggered structures are where all of the bonds on 2 adjacent atoms are kind of out of each other's way. Eclipsing structure, these are where the bonds are bumping into each other. And they repel because electrons in the carbon-hydrogen bond on the front, this guy here, and the carbon-hydrogen bond in the back, since they have the same charge, we get coulombic interactions. So as a result of that, they'll be higher in energy. We just drew this before. The video we showed was that this can, imagine it rotates, it's freely rotating around. Each time it passes through one of those CC interactions as eclipsing, staggered, eclipsing, staggered. They each have the same maximum and minima. And as you rotate this through, every time we hit that minima, continuing to rotate takes us back to a maximum. So that's where we get an angle diagram that looks like this. 0 is the angle that we make when we have our 2 carbon-hydrogen bonds. We pick any 2, and we say that they're lined up with each other. If we do rotation in either the positive or negative direction, we start lowering that energy because we proceed towards a staggered structure. The most important thing to get off of this graph, the maxima you see correspond to eclipsing structures. The minima are all staggered structures. The other thing we get from this profile, every staggered structure is the same low energy. Every eclipsing structure is the same high energy. After we pass that minus 180, we're moving back on the other side of the dihedral. So it's a circular repetition. The period, each of these, is 60 degrees between each maximum and minimum. And that's just walking through that bonding angle of our dihedral. So to go from minima, it's 120. 2 rotations, min, max each time, okay? And then, yeah, we've tried to calibrate this too. Basically, each carbon-hydrogen bond, that interaction, while bad, they can sum up. So if you look on your energy axis, notice the maxima is about 12. We just said carbon-hydrogen bonds are worth about 4. Why is it 12? How many carbon-hydrogen bonds do you have? There's 3. These are additive interactions. What you'll notice is if each carbon-hydrogen bond is worth about 4 kilocalories of energy, around ethane here, you have 1, 2, 3. That's 3 possible eclipsing interactions that are just carbon-hydrogens. Total sum's 12. What that means is as we change these, as we change them into different structures, they may be larger or smaller, but there's still this summation. And this is why we keep track of these. The barriers of rotation can tell us about what's actually around some of these centers. One of the other ways, last one we have to talk about in terms of projections, we've got our line bond. That's our normal sort of flat on, where the bonds are in plane. We have Newman, that's looking down the axis of the bond. Sawhorse projection is one more that you see. What we're doing here is we're sort of canting the angle at the, sort of this forward projection. You're still trying to give an angle of perspective, where it's drawn like this. It's called a sawhorse because it's got sort of a back, a spine in between, legs in the front, legs in the back. So we're sort of drawing it. This part here is meant to show that it's descending back into the page, but you're looking at something in sort of a semi-perspective angle. This is a useful perspective for some kinds of natural products, just because as molecules get more and more complicated, We're challenged with ways of representing a fully three-dimensional structure on a two-dimensional page. And we need to communicate clearly to do that. So these are our other sort of tools in perspective. But if you see something that looks like this, everything is a simple line. It doesn't have wedges and dashes, but we've got this sort of down off to the side, this kind of these weird kind of looking bonding angles. This is correct. It's what's known as sawhorse projection. And again, what we're really trying to say is this atom is closer to you, this one is further away, right? It's towards the back into the page. So it's a perspective diagram. Again, it's called sawhorse because if anybody's done woodworking or something, this kind of angle sawhorse, legs with a spine is kind of what we're meant to sort of project. You can still show both eclipsing and staggered in these geometries. So eclipsing here, you notice that these two pieces are aligned with each other. In the staggered structure, we have this 180-degree opposite presentation between the two. So we can still emphasize that one is higher or lower in energy. It's just this is what they look like. Again, Newman is far more clear, right? We can be unambiguous about what's going on and which structure we have. The same is trying to be shown here in this point. The thing I want to mention, though, is do not mix. You do not mix different formalisms. If you're drawing in staggered projection, or sorry, sawhorse projection, you're not going to add wedge and dash bonds to this. Wedge and dash is specifically for 2D line bond structures where you're looking side on to it. Sawhorse is meant to say, look, we're already putting perspective into it by how we've drawn these things, how we've chosen to. The other thing that's going to be really helpful, as molecules get more complicated, you have more carbons associated with them, and if we're going to draw what looks like in normal sort of 2D wedge dash, or like the line bond structure, drawing it in these kind of alternative perspectives, what the choice is, when you go to something like sawhorse, or you go to something like Newman, you're choosing one bond among many to focus on to talk about what's happening locally. So in the cases we've had now, it's just ethane. But as the things that substitute, the front or back carbon, get more complicated, there's chlorines, many carbons. It's very useful now, instead of having to draw out the CH2, 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 or long line bond structures on the molecule, you condense them using simple abbreviations that we've had here. So methyl, instead of using CH3, you can use Me. 2 carbons, ethyl, ET. Propyl. Isopropyl is IPR. So that's the attachment of a 3-carbon substituent via that middle carbon, the secondary carbon as it is. So these are really, really, really useful and sort of a tool to make your drawings more condensed and allow you to sort of focus in on one part, because you're not drawing the spaghetti or fruit, all the rest of the molecule. You're focusing on a single bond and its geometry. So do know these. These are highly, highly, highly useful. You're not wrong if you use these structures. The problem if you start to rely only on the sort of extended line bond or the molecular CH2, 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 it's very easy when you're moving very quickly to suddenly draw a structure and forget to put in one carbon. If you're doing that and you just know, oh, I looked at the structure, I'm recopying it, I'm banging along super fast, and you just write CH2, CH3, you've just committed alchemy. You deleted a carbon. This isn't the same molecule. No points. So that's why going slowly, carefully, or using these can be super beneficial because they're less prone to error, okay? So let's use this. Here we have a molecule. What we're going to practice is moving back and forth between these perspective rotations. And there's a number of different ways to do this. I'm going to show you what I like or how I learned this. So what we're asked to do is we have 2D line bond, right? This is our wedge dash notation. This is telling us something about both geometry, is it eclipsed or staggered, but it's also telling us relative position. Now there's a correct way to take this and convert it to our Newman projection. So this is where mental mind map, you take this molecule, you're going to spin it and reorient it from a different perspective. The other thing too that helps you a lot, this is where your model kits are useful. So starting today, I'm starting to bring my model kit for all our stuff. As an example, So doing this on paper, how we do this is I first of all have to choose what direction I'm going to cite. If I'm going to draw this to Newman projection, this is the bond I'm going to consider, and I choose to look this way. So this is my super creepy eye. I'm going to look down that axis. Now, if the question does not tell you which way to look, it is up to you to define it. You can choose either way. So we could choose this one as well, open-ended. I'm going to choose to do the first. Okay, that means I'm looking at this front carbon. More importantly, that front carbon has a methyl, a chloro, and a hydrogen. I've color-coded those three for solid point. If I'm going to look down that bond, the first thing I'm going to do is say, look, I'm looking from here. I'm going to draw my template. I'm looking at this front center. More importantly, I now have to draw a Newman projection, so I'm going to use a template from the Newman projection. The front carbon has 3 lines in a Y that are crossing the outward bond. In back, I have my staggered one. Now, I've chosen to draw staggered. Why does that make sense? Based on how this molecule is drawn, this is the template I would start to build off. Why did I do that? What do you see that says, yeah, that's the right one to do, instead of looking at an eclipsing structure, for example? Yeah? Exactly. We have this bond that is in the plane and this bond that is in the plane are 180 degrees to each other. They're pointing opposite. That is how you represent a staggered structure in 2D. So I'm going to start by drawing a staggered structure in my Newman. More importantly, what I'm going to do now mentally, if you look at your 2D structure, in your mind, if I'm looking down on top of it, what is coming towards you? Just looking at the one we're highlighting with that green dot, what atom or element is coming towards you on that center? What's a wedge? Methyl, hydrogen, or chlorine? Methyl. The methyl is coming up towards you, meaning down in the page is your hydrogen. Off here, like in the plane of the page, that's my chlorine. So if I'm standing over top of it and I need to turn it, it's basically like taking the molecule, sitting flat. I need to grab it with my left hand on methyl. I need to reach through the page, right hand. I'm grabbing my hydrogen, and I have to pick it up. The reason why is because the methyl's already above the page. I'm going to tip it over this way. I'm taking the molecule as you've drawn it, and imagine sort of just flopping it over, picking it up, and rocking it to my left. So if I were to hold the methyl with my right hand, or excuse me, hold the methyl with my left hand, hold the hydrogen reaching into the page with my right, what that would do is I would put my methyl here, I would put my hydrogen here, and I would put my chlorine there. Now, remember, this is a circle, right? I could redraw this, methyl, hydrogen, chlorine, in a 360-degree rotation. As long as the relative positioning you've drawn here is correct, in other words, from hydrogen, as I move clockwise, I run into chlorine. Continuing clockwise, I run into methyl. That relative orientation has to be correct. It would be incorrect to leave chlorine at the bottom, put methyl where hydrogen is, and hydrogen where methyl is. If you just invert those, that is not the same molecule. So this is where, again, mentally, grab methyl with my left, hydrogen with my right, pick it up, plop it down. This is what I have. Everybody see that? Next thing, if you look at the back group, what I usually like to do is you use groups that are along a common plane. Remember, the plane of the molecule, this here, where we've got a chlorine and ethyl group, that defines the plane of the page. That's kind of cutting through the middle of the molecule, which means anything above it is on the same side, anything below it is on the same side, relative to each other. This plane of the page, when I'm actually over here, that plane is right here. We've picked up this molecule, we've ended it on its side, and I've now bisected. The plane used to be right through the middle of it. So when I'm looking at Newman projection, what used to be the plane this way is now standing straight up and down here. Which means anything on one side, if it used to be on one side, it's still on that same side. Methyl was up. What else is up on this back carbon behind it? Methyl was up. What else is? Hydrogen. So that has to be here. the relative positioning of these two groups, because they were both above the plane, can be used to help define it. Same thing, on the back carbon, hydrogen was back, bromine is back. That puts bromine in this position here. And in the same plane of the page, chlorine, ethyl, that puts ethyl group on the back carbon in that same one. So there's two exercises you're doing. What atoms or elements are on the front carbon? In this case, looking where my eye is, it's methyl, chlorine, hydrogen. If I define the plane of the page, what's above and below it? So again, mentally, grab the methyl with the left, grab the hydrogen with the right, tip it up, plop it down onto the desk, and look down on top of it. Methyl and hydrogen are both towards you, so they'll be on the same relative plane here. The only difference is that second blue hydrogen is on the back carbon. Hydrogen, orange on the front, bromine on the back, those are the same plane as well. So most importantly, where you put them, what you're doing by putting the bromine here indicates it's on the rear carbon. How does that feel? Cool. Again, this is one way to do this. If you've learned a different way, if you're used to sort of a different perspective, that's fine. This is how I work through it because, again, it allows me to sort of mentally go through a systemic way, pick them up and rotate them. Now let's go the opposite direction. You start with Newman, you go back to line bond. This is walking in that inverse direction. Now we're looking at something where the plane here, what we're going to build, we're already looking at the plane of the page. We also notice this is already staggered. So the template I'm going to be using here would look something like this. That is the plane of the atoms I'm doing, and what I'm going to do for reference here, this is the opposite direction of what I just did. Instead of looking at this carbon here, I'm down on top of it. I'm going to take that Newman projection and I'm going to tip it to my right. I'm going to sort of grab, in this case, my hydrogen here in the front and my nitrogen, and I'm going to rock it over that way. That puts this center here as what used to be the one I was looking at. You could go either direction. If you like to rock it to the left, that's fine, or to the right, not a problem. But be systematic. So if I'm looking at it this perspective here, it's like I'm taking this whole thing and sort of flopping it down that direction. This is my same common one. The reason I've chosen this propyl group here is because it puts it in this position. What is, from my Newman perspective, what's 180 degrees from the propyl? On the back, what is it? Yeah, it's my ethyl group. Ethyl group here is 180 degrees to my propyl. That builds up my template. Once we're here, we know no matter where we put everything else, the front carbon must have a wedge and a dash. The back carbon must have a wedge and a dash. So you notice one of the things I'm doing, all of these things, Newman projections have a blank template. Line bonds have a blank template. Do yourself a favor and start by drawing this out. Instead of trying to figure out everything at the same time, start with the basic skeleton structure, populate the individual positions, okay? So if I'm looking now at this front carbon, I've labeled green. I have a nitrogen, which was over to my right, and I have a hydrogen that's on my left. If I've flopped it down this way, again, I'm going to imagine mentally, I'm grabbing the orange hydrogen with my left hand, I'm grabbing the blue nitrogen with my right hand, and I'm twisting it. My right hand is going to go into the page. My left hand hydrogen stays above. So this will be my hydrogen. This will be my nitrogen. Once I've gotten that fine and I'm happy with this, you can use relative notation or relative positioning to fill in the last parts. If this was the plane bisecting down this way, nitrogen and this blue hydrogen were on the same side, and this orange hydrogen, that nitrogen back there, on the same side. So I'm going to put an NH2 here and hydrogen back here. Most importantly, again, everything has to be self-consistent. If you look at your Newman structure, one nitrogen on the rear carbon goes one way, one nitrogen on the front carbon goes the other way. They're on opposite sides of the plane that would be bisecting down the middle of this molecule. Propane and ethyl, top and bottom, are 180 degrees to each other. They make up that sort of opposite sides of that Z that we make for our bonding axis between them. How's that feel? Practice is the key here. And again, go slow. If this is at all bugging you, your model kit is your savior. And what it is about is being able to translate from this structure here to your populated model. And again, you don't need to build, let's say, a propyl, 3 carbons. You don't need to build an ethyl, 2 carbons. You just need to sort of color code parts of this basic template. And in your mind, you say, all right, I'm looking at this Newman structure, the propyl, I'm going to use a green atom to denote my propyl structure. Boop, put it there. I'm going to use a yellow atom to denote my hydrogen, whatever you want. And if you color code them that way, it's a lot easier to manipulate. You don't have to spend all this time constructing chunks of your molecule. It doesn't have to be fully accurate, just needs to be noted, right? The other thing that helps you with this too is, again, being able to sort of walk through this in different directions. If you practice this and you're happy with it and you're like, yes, I've got it, try drawing it from the other perspective. What would this look like? Same guy. If I took this and instead of rotating it to my right, if I flopped it to the left, what would this look like now? So I still need to have the stuff in the plane. If I were to sort of flop it this way, I'm now going to have something that I'm going to draw like that. Different lightning bolt. I'm going to put my propyl here, and I'm going to put my ethyl there. Where once again, this is that common one. That was the one I was looking at. Notice that the structure here only starts to take shape once you've made a decision. I'm going to move to the right. I'm going to put one group down. As soon as the propyl's in place, everything else starts to click into place after that. Once I've defined where the propyl is, the ethyl must be over here to this perspective. The one I was looking at the front, the here in green, is now over to my left. All right, so let's fill it out. I'm going to have a wedge and a dash, a wedge, and a dash. What's on the wedge position on this one? Based on how I've done this, what do I have? Hydrogen, nitrogen, carbon. Nitrogen. It's my NH2. By taking this and flopping it that way, that would be my, based on my color code, it's my blue NH2, which means my hydrogen will be this one over here. In orange, went into the plane, hydrogen and NH2. Notice if you look at these two, what we're looking at there is the same molecule doing what's called a pancake flip. If I take the molecule on the top right, I were to scoop it up, like imagine I'm flipping a pancake, scoop it up, flip it all over, put it down, I get the one here on the bottom. The propyl is moving from the right-hand side of the molecule to the left hand. The two groups that were towards you, the orange groups, are now, instead of out of the page, they're into the page, and vice versa. The two that were in the page are now pointing towards you. You've just literally taken this molecule and turned it over, okay? So these kinds of manipulations, rotations are helpful. Any other questions on that? Who is like, this is like the best video game ever? Well, okay, not fun, in a perspective of like, what is going on? Little bit. Okay, let's practice it. Let's say you have this molecule. Here's my creepy eye. That's the direction I'm looking at it. Which one of these structures is the correct one? Now, one note. What is D? You notice on the front carbon, we have hydrogen, 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 different colors. Back carbon, we've got this green D. What is D? Deuterium. It's a heavy hydrogen. It's an element or a way for us to code or identify this is not the same hydrogen, it's a label, an isotopic label. So, take a second, freeze one in your head. Okay, now turn to the person next to you, argue this out. Do this by a process of elimination. You should be able to knock out a couple of them as that can't be right very quickly. So instead of jumping right to the answer, again, frame one in your head. You're pretty sure you got the answer. Give me one that it absolutely could not be.
D.
Okay, D. Why is D out? It's eclipsed. Your structure at the top is staggered. You can see that because hydrogen on the carbon that's closest to you is pointing up. The methyl group in gray at the back is down. You're in this walk like an Egyptian kind of pose, right? Front and back. That is staggered. This corresponds to eclipsing. Not the right answer. Okay. Give me another one you can knock out. What is another one that it absolutely could not be? Okay, we got C. Why is C out? Right. The front carbon you are looking at here in C has attached to it a deuterium, a hydrogen, and a hydrogen. That would be kind of like looking here, right? Because you're looking at this deuterium on this one. More importantly, what is the constituents attached to the same carbon that has the deuterium? It is composed of a deuterium, a hydrogen, and a... And this one has deuterium, hydrogen, hydrogen. Not even the same molecule. This is the wrong carbon, and these do not correspond to the constituents attaching to that center. That's out. All right, give me another one you can knock out. A. Why? Yeah, same thing. You're looking at the carbon with the deuterium. That's out. All right, we're down to B and D. E. Which one is it? Okay, unfortunately, those both sound very similar. Which? Okay, give me a quick way. What is one thing you can look at, your molecule, that you say, I am looking for this feature? The CH3. Do both have CH3s in the back? Yeah. Okay, so perspective is good. What is attaching to the carbon you are looking at? Hydrogen, 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 in what colors? Yes? Okay, that's one. Red hydrogen should be pointing up, and red hydrogen is what perspective relative to your methyl? Yeah, like basically, this hydrogen and this methyl are 180. I'm looking for something where red hydrogen and gray methyl are opposite each other. I see that here. This is too close. Yes? Could be. So, like in the end, in this case, this is nicely lined up where the hydrogen is up, this is up, everything is okay. But remember, these are circular symmetric. Is this molecule, if I took B here, is it the same molecule if I took the whole picture and just rotated on its side? That's the same thing. That's okay. So this relative positioning will not lead you opposite. Even if B was rotated 180 degrees, the hydrogen and the methyl, if all of them rotate, right, then they're always opposite. If you only rotate the front carbon, that's a different conformation. Okay, we will do this one next time. I want to work through that after. But you guys should be masters of this going through. And again, elimination really helps you here. Yes?
So on the last question, could we switch which one is like to the left and which one's to the right as long as we do it on both sides, or would that be wrong because of the layer?
That would be wrong. If you switch both on both, that's a whole different molecule. Okay. You're looking at a mirror image in that case. Okay. Yeah. Okay, slightly more complicated structures. In the same way we've talked about eclipsing and staggered, as the molecules get more complicated, you still have eclipsing and staggered. The energetic consequences, though, are slightly different. Remember when we talked about ethane? As you spin around ethane, every single carbon-hydrogen eclipsing interaction is identical. When you go to butane, you now have a methyl and two hydrogens. What happens now is as you go around this circle, if you take the dihedral angle between the two carbon-carbon bonds, we start at the top. That is an eclipsing structure, but we give it a special name. Here, this eclipsing structure, we call it SYN, S-Y-N. As we move, this is now a staggered structure. This is eclipsing. This would be, again, eclipsing, staggered, eclipsing, and staggered. So it will still go through the same rotation. Every 60 degrees, you're into one of these lower high energy ones. From what we know before, which are high energy? Eclipsing or staggered? Eclipsing. Staggered, low energy. The difference now is if they're not symmetric, if not all of the different positions are the same, these are not exactly equal. Some are higher in energy than others. Some eclipsing are worse than others. Syn is particularly bad. Why? What's special about that? It's completely eclipsed. They all have eclipsing. But what is different now? We've got this index. The methyl group is physically bigger than a hydrogen. This is what's called steric interaction. So it's nice. Welcome to Vancouver. It rains a lot here. Who's been walking around with their umbrella? You guys are significantly shorter than me. If I was to walk past you on the bus stop and you have your umbrellas out, I will be decapitated. What happens is big groups, especially if they spread out sideways, will bump into other groups. The methyl group, think of it like a little umbrella. If those two carbons on either side have a methyl, you have these two umbrellas. When they're sitting, where they are both eclipsing each other, not only do you have the bond, the carbon-carbon bond, front and back lining up with each other, that's our bond strain, that's the bond interaction, but now you have this added strain. The added strain we have here is the methyl group, the sort of lateral projection of these hydrogens that are bumping into the other methyl group. So in addition to this bonding interaction, you think the syn has two kinds of pain. It has bonds bumping into bonds and steric strain, which is groups bumping into groups. The methyl group physically bumps into the other methyl group. And again, it's still electron repulsion, but because we have this larger cloud, because the CH3 spreads out sideways, again, think of an umbrella, they're going to be worse in that one. As a result, we give it a special name. This is the worst interaction, the worst eclipsing. It gets the name syn. Then we have, this is staggered, this is staggered. They're lower in energy, but they're not the lowest. The lowest of all the energy is this one down here. We call it anti. That's where all the bonds are out of the way of bonds. It's not eclipsing. And the groups are out of the way of large groups. The two umbrellas, one's pointing that way, one's pointing this way. It's this beautiful pirouette, right? What's happening there is the groups are as far away as you can. That's the lowest we can possibly be, because if we continue to rotate, this group begins to approach that one as well. The energy will increase. So we have a special name for our lowest energy, staggered. We call it anti. The two groups are as far away as they can. The middle two, staggered ones, also get a special name called gauche. These are low energy points. They're just not the lowest, because this gauche here has another interaction that's missing here. If you think about this, we have two kinds of strain. Bonds bump with bonds, groups bump with groups. Every eclipsing structure, bonds bump with bonds. Syn, you have bonds and groups together. Gauche, no bonds, but you do have groups. The two methyl groups, while not directly eclipsing overlapping, are still close by. This is standing near somebody that has an umbrella out. They're not directly in each other's face, but it's still worse than being nicely, this is social distancing. Does that make sense? It's about lateral projection. We give it this special name gauche because we're saying, yes, it is staggered. It's just not as good as it could be. Does anybody know what gauche means? Heard of? To the left, French. What you'll start to notice is organic chemistry is highly left-phobic. Gauche in sort of like proper culture usually means you're weird. You're just a little bit off. If you are gauche, then you wear white after Labor Day, things like that. So it's not quite right, basically. It's not as good as it could be. So what we're introducing now is we go beyond just simple carbon and hydrogens. We not only have steric strain, but we also have this bond strain. Steric strain is specifically carbons with carbons. As a result, we get a different energy profile. If you're going to fill this out, notice the highest high right here. This would be our syn structure. That's where we have both bonds and groups, steric and torsional strain. Down here at the bottom, this is our gauche. It's a low energy structure. It is it's not eclipsing, but there's steric strain. Then we go back to our other eclipsing structure. And then finally, nice and low, this is our anti. There is not a special name for that eclipsing. It's just eclipsing. Bad eclipsing, we call syn. Very, very, very good staggered, we call anti. Not so good staggered, we call gauche. But notice here, the energy difference, this little gap right here between minimum at 3 and minimum at 1, that's the measured amount of energy that is just due to what? What is a... Yeah, perfect. Here at 1, no groups, no bonds. At 2, just bonds. At 3, no bonds, just groups. At 4, all pain, groups and bonds. So we have this additive thing. By going through this rotation, we have different permutations of energy that are due to just different kinds of interactions. What this teaches us is, yeah, groups with groups are bad, bonds with bonds are worse. And what this is trying to emphasize is steric strain is a very local phenomenon. Who's played Warcraft? Like old school, good Warcraft, not online world of, StarCraft? Yep. There you go. Notice when you go to StarCraft map, there's what's called the fog of war. You can see what's around you. That's the same thing here. Steric things can only see things that are nearby. It doesn't care very far away. That drops off very quickly. So it's a very local interaction, okay? All right, so if you had to order these in terms of energy, what's worse, what's middle, what's best? Sorry. Eclipse is groups, no, bonds with no groups. Just eclipse is bonds on top of bonds. Okay. Once again, process of elimination. Of these 4, which is the worst? Can everybody agree which one is absolutely the worst one here? That is Z. Not Z. Z? Oh, God. I taught in the States for so long, it totally messes me up. I apologize. Which is it? What's Canadian again? I just lost it. Somebody's messing me up. Okay. Z. Y. We got, this is both eclipsing and big groups near big groups, right? That's going to be the worst. And what's nice about finding that one's can jump out at you. That's gone, that's gone, that's gone. The worst has to be Z. We can now bring it down to 2. Okay, what's the best of these? W. Okay, no help there, right? So what between X and Y, which do you think is worse? Y. Okay, we got 1 vote for X, we have 1 vote for Y. Y, present your case.
Groups are closer in Y.
Groups are closer in Y.
No, it's going to be X.
Okay, so Y has just rested his case and walked away. X's have it. Why is it X?
X is bond strain.
Bonds are worse, right? If you go back to this, bonds pay a higher price than groups. So I would agree. Eclipsing sucks, right? Eclipsing will always be a maximum energy. If you can get to staggered, that will always be better, and then it's just ranking staggered. So this is where size matters. Bulkier groups will produce more steric strain, and it's really this factor that we look at our energy barriers. So if you look at these two, actually, we'll come back to that one. One thing I do want to touch on, though, is this idea there's one more kind of strain. So groups bump with groups, bonds bump with bonds. This is what we call cyclic structures. Remember, the normal bond angle as we move through here, these are all sp3 centers. In a normal sp3 center, what we're going to have is what geometry around that carbon? What is the bonding angle you're hoping to get? Tetrahedral, which is what angle? 109. Okay. Move from right to left, something like cyclopropane has a buttload of steric strain, or sorry, bond strain. And it begins to go down and down until you hit cyclohexane. Cyclohexane is the first structure in the sequence that has 0 ring strain. It still has some strains, you'll notice, and we'll go through this part, but basically once we're at cyclohexane, it's basically equivalent to a linear molecule. It's very happy in this sort of geometry. We have the nice sort of presentation where all bonds are at their optimal angle with no compression or any point. That's why these become so important. If we have this nice 109-degree angle, the angle strain is minimized, and that's why nature uses 5- and 6-membered rings very frequently. They're great ways to sort of present structures. This is why you see 6-membered rings like this in, what's the most common biomolecule you've seen with 6-membered rings? Probably. Well, benzene is somewhat bio. Again, I wouldn't bathe in it. Give me something else, a different molecule. You probably had it for breakfast. Glucose, sugars. Sugars are very common cyclohexane-like structures, right? They're the 6-member type rings. So this is where we get these heats of combustions. This all comes as a consequence of stored energy. What we're trying to emphasize here is as you go down and compress this ring, just like our ring strains, we can actually measure this as we go through it. What you notice is, as we get beyond this one, as we start to crack it, what we're looking at here is the average amount of energy you get per carbon-hydrogen pair. And normally in cyclopropane, you get way more back than you would at cyclohexane. Cyclohexane, you're at 653. At cyclopropane, 697. That difference in energy, that extra sort of between 695 and 650, that's the ring energy, the ring strain that you've got. It's the extra destabilization that's happening because of this ring point. You go beyond that, it's basically about 650 something each time. That's all we're trying to do. Now, cyclohexanes are special, not only because we have to know a lot about them, but we've got these different presentations. Line bond structure, wedge and dash, is how we would look at it here on the left. But most importantly, we have these chair conformations in the middle. Chair conformations are trying to say, whoops,